Hi everyone. Today we're going to be talking about the heat equation. And the heat equation is a way of describing how a temperature distribution over a physical object varies as time moves. And that means there's going to be more than one variable involved because we need one variable to describe the spatial distribution of the temperature and another variable that describes how things change with respect to time. So the heat equation is actually an example of something called a partial differential equation. And so this is the launching point not only for why Fourier series were invented in the first place, but also the subject of partial differential equations, which are really the language that we need to describe many physical scenarios. So to give you the setup for this, we have a metal rod, x is equal to 0, x is equal to 1. So we think about this as a metal rod, if we're thinking about it in terms of the way that Fourier thought about it. And over that metal rod, we have an initial distribution of temperature. So this is a temperature distribution. We think about this as being f of x. It's in x and not t because this is a spatial distribution. So I'm starting with a metal rod that starts at 0 and ends at 1, and sitting over the top of it, there's some distribution of temperature that I've measured somehow, or I've induced in the rod. Maybe I heated it up with a flamethrower or something. Now, if you want a derivation of where the heat equation comes from, Osgood has a very good one in his notes. We're going to start with the heat equation, and then from that, we're going to show how Fourier series can be used to solve it. What the heat equation says is that if I let U of x and t be equal to the temperature at position x and time t, we can describe the evolution. We can describe the evolution of the temperature with this differential equation, which is really just an application of Newton's law of cooling. The time derivative of u is proportional to the second spatial derivative of u. So if you want some idea of what that actually means, what we're measuring here, or what we're saying, is that heat flow, that in some sense this is a measurement of heat flow, right? Change in temperature is a measurement of heat flow, is proportional to the shape of the graph, not just the slope, but the rate at which the slopes are changing. So concavity of the graph is proportional to the heat flow. So this is just Newton's law of cooling in a sort of fancified version. But what we're measuring with the heat equation is transfer of heat energy from one spot in the rod to another spot as time goes on. So the heat equation, or what we call the 1D heat equation, is just ut is equal to minus k uxx. If you're wondering what this constant is doing in here, this is related to thermal resistance. So it comes out of the physical properties of the particular object that you're studying. So the goal of this is to try to figure out a way to write down a formula for u of x and t. And the particular case that Fourier studied was the case where the 1D rod was actually not just a straight line, it was a circle that had been bent around and connected to itself. So Fourier considered a rod that looked like this. So he took x is equal to 0 and he glued it on to x is equal to 1. So that as you go around the circle, you have the temperature distribution sitting on top of it that looks like, say, like the way I drew it earlier, was it spikes up right here, and then it kind of comes down and it wraps around the circle like this, and then it sort of falls down and comes back to 0. But the idea is that there's a distribution on the ring. So you think about this as f of x, and that peak right there For us, that's sort of a high point in temperature. So from this scenario, what can we do to solve the equation ut is equal to minus k uxx? What sort of approach can we take? If we have a really powerful approach, we should be able to handle any f of t that I distribute on the ring. So I don't want to have to necessarily do it for specific cases of initial conditions. I want to be able to solve this for any f of t that I stick down on the metal ring. So what Fourier realized was that if you took the distribution of temperature on the ring and you graphed it, and you thought about the ring as being parametrized not by some sort of left-right spatial dimension, but thinking about it in terms of angle, where we travel around the circle this way, and then you plotted f of t, what you would end up with if you kept going around and around the circle would be a graph that looked like this. So if this is x is equal to 0, you would do a distribution of f, and then you would get to x is equal to 1. But there's nothing stopping you from continuing to wrap around the circle. And so Fourier's big insight was this means that the temperature distribution is periodic spatially if we think of our variable as measuring the angle as we go around the circle. So the temperature distribution is periodic in space because I can just wrap around the circle over and over again. And periodic in space means that perhaps this is amenable to thinking about it in terms of sines and cosines. And so Fourier's big leap was to say maybe what that means is that the spatial part of u is built up from sines and cosines. Because to me, that looks an awful lot like sines and cosines. So here's what he assumed the form of the equation looks like. So in the back of your mind, I want you to remember that the equation that we're trying to solve is ut is equal to minus k uxx. By choosing units, we can always choose any value of k in this equation that we want, and then we can scale our functions. So we really only need to solve this for one case of k. And so we can arrange, if we like, that as long as we can solve the equation ut is equal to 1/2 of uxx, then we're golden. So we're going to look at this specific case with our initial condition that u of x and 0 is equal to f of x. Fourier's big insight was to guess, and it was a guess. It took a long time after this to show that this was rigorous, but it worked in understanding what was going on. And so to applied mathematicians and engineers and scientists and even the mathematicians of the day, if something worked, that was justification for doing it. Fourier's guess was that u is equal to the sum from n is equal to minus infinity to infinity of Cn of t e to the minus 2 pi I n x. So he split the behavior of the solution into two parts. A spatial periodic part, so this is sort of spatial and periodic, and then constants that evolve as time goes on to account for the fact that this function is changing. So this depends on time. And that's it. There's a Fourier series. And it's a Fourier series for which we know how to compute these Cn of t's. Yeah, sure, there's a t involved, but the equation doesn't change from the way that we originally solved it. So let's plug it in. If u is equal to the sum from minus infinity to infinity of Cn of t, so those are the coefficients that evolve with respect to time, times e to the 2 pi I n x, that's not supposed to be negative, Cn of t e to the 2 pi n x, Then, and we want to plug that into ut is equal to 1/2 uxx. We actually need these derivatives. If we take a derivative of u with respect to t, well, that's pretty easy. Ut is just equal to the sum from minus infinity to infinity of c prime n of t. So whatever that function is, it's got a derivative. And this is unchanged. This is beautiful, actually, because these variables are separate, right? There's a t part and an x part. So this is like using separation of variables, but it's already done for us because we've guessed the form of the solution. And uxx, that is the second spatial derivative, will mean taking the derivative of that exponential twice. And what we end up here is the sum from minus infinity to infinity of Cn of t. That's unchanged because it's only a function of t times 4 pi squared n squared, and then I squared is -1, so there's a negative in here. E to the 2 pi I n x. So that's just the result of taking a second derivative of this, which drops the exponent down twice. We can just plug that into the differential equation. So now we're going to take these two things and we're going to put them into this. Now that we have expressions for ut and uxx, we can plug them into the differential equation. Ut is equal to 1/2 uxx. And what we'll end up with is the sum from n is equal to minus infinity to infinity of Cn prime of t e to the 2 pi nx is equal to 1/2 of the sum from n is equal to minus infinity to infinity of Cn of t times minus 4 pi squared n squared e to the 2 pi I nx. Since these series have the same terms, so these terms match and their indexing matches, and that means these series can only be equal, especially because the complex exponentials are orthogonal, right? Since complex exponentials are orthogonal, two series of them can only be equal when their coefficients match. And that means that I can reduce this problem to a problem of the coefficients. Cn prime of t is equal to -2 pi squared n squared Cn of t. And this is an ordinary differential equation. And not only is it ordinary, it's separable. It's the easiest possible kind of ordinary differential equation. When you separate it, you end up with this. And after you get a separation, the way you solve is you integrate. So let's look at the integral of Cn prime over Cn is equal to the integral of 2 pi squared n squared negative. Remember, this is really secretly a dt integral, and this over here is like a dc integral. Then you're going to get the natural log of Cn is equal to -2 pi squared n squared t plus a constant of integration c. Then you can e both sides. And after doing the algebra to reduce this, you get Cn is equal to k e to the -2 pi squared n squared t. But the awesome thing is that I know what k is. And I know what k is because I know the initial distribution of temperature. I know that u of x and 0 is f of x. And if I use that, well, that's also supposed to be equal to the sum from minus infinity to infinity of Cn of 0 e to the 2 pi I n x. But that's just writing f of x as a Fourier series. And that means that Cn of 0, which is just k, is the nth Fourier coefficient of the original distribution. That's amazing. But not surprising. If we're going to represent the solution as a Fourier series, we expect that the Fourier coefficients of the initial temperature distribution have to come into play somehow. So where are we? What we've arrived at is this. We started with u of x and t, guessing that this was equal to the sum from n is equal to minus infinity to infinity of Cn of t e to the 2 pi I n x. then we guessed, then from this form and plugging into the differential equation, what we found was that this is equal to the sum from n is equal to minus infinity to infinity of k e to the minus 2 pi squared n squared t e to the 2 pi I n x. But we could go one step further and use our initial condition to show that this was equal to the sum from n is equal to minus infinity to infinity of f hat of n e to the minus 2 pi squared n squared t e to the 2 pi I n x. And this is the general solution to the heat equation. So the general solution to the heat equation involves three pieces: the Fourier coefficients of the original distribution, a piece that evolves the equation as time goes on, and a piece that controls the spatial distribution around the ring of the temperature distribution. And that's it. This is amazing that this works. Absolutely outstanding. And the specific approach was motivated by the fact that we were working on a ring, but we're going to show in the next couple of lectures that we can take this basic idea and actually extend it to functions where we think of non-periodic functions as being sort of periodic, but of length infinity or period infinity. So this is a profound accomplishment in mathematics. So in summation, if I have the heat equation ut is equal to 1/2 uxx, and I have the initial condition that u of x and 0 is some function f of x, then the temperature distribution is equal to the sum from n is equal to minus infinity to infinity of the Fourier coefficients of the distribution e to the minus 2 pi squared n squared t e to the 2 pi I n x. Remember, a spatial component, a time component, and something that corresponds to the initial conditions. Now, what I'd like to show you is what this actually looks like when you model this with mathematical software. So it's not just some abstract formula, but something you can actually use to compute. So this is a demonstration that I did in Mathematica. And what we're looking at here is this black ring that I've drawn in 3 dimensions is supposed to represent the ring that we're doing our computations on. And then the red curve, that's our initial temperature distribution, f of x. And in this case, it's the function 1 over pi squared, 2 pi x minus pi squared. So that's an initial temperature distribution with this as our f of x. That is, this is the function that is defining the temperature distribution. Now I'm using a fancy function that Mathematica has called Fourier coefficient to just compute the Fourier coefficients for me. And that's all that this does. And it gives me a formula for the Fourier coefficients. Once I have that, well, underneath it, I just checked a spectral plot of the original, of the function in order to just see what the frequencies that were present in f of x were. So this is a plot, a two-sided plot of the Fourier coefficients. Then all I did was I built u of x and t using the formula we just did. Now I can't do from minus infinity to infinity, but I did 10 terms, so from minus 10 to 10. And you can see the exact form of the answer that we built is right here. This is Cn of t. Then I've got e to the minus 2 pi squared j squared t. Then I've got the space component, e to the 2 pi I jx. And then I built myself a manipulate environment where I can see the ring is in black and the initial temperature distribution is in red. The Fourier series at time is equal to 0, that's the blue curve. And you should be able to see here that the blue curve and the red curve pretty much exactly correspond. So my Fourier approximation is pretty good, except maybe at this little corner right here in the original curve. Now what happens as time goes on? As we start moving through time, you can see that's what happens is the heat starts to disperse itself equally over the ring. And in the long run, what happens is the temperature of each element in the ring becomes equal, which is exactly what we expect to happen from Newton's law of cooling. that if I start with a really asymmetrical, uneven distribution of temperature, that asymptotically what should happen is the temperature should spread itself evenly out over the ring. Okay? And that's contained in the form of the solution to the heat equation. The reason that we have an averaging in temperature that shows up in our solution is not just related to the fact that if we observe the physical world, we can see that that's what happens, that temperatures average out until there's no heat flow in or out because the two objects settle in at some relative amount of heat distribution that makes the temperatures equal. The equation itself, or this solution, holds that information in it because this term disappears as t goes to infinity. Now, if this term disappears because e to the minus infinity is 0, then that kills all of the rest of these terms as well. And so in the limit, what happens, if you take a limit as t goes to infinity, e to the minus 2 pi squared n squared t goes to 0. And so the only term that survives in the sum is just f hat of 0, the 0th term. But that's just the average temperature. It's the average of the function. So everywhere on the ring, as time goes to infinity, the temperature is just the average of the original temperature distribution. And that should make sense. No matter how much heat is dispersed throughout the ring in whatever uneven way that you want, in the long run, what's going to happen is all that heat energy is going to distribute itself evenly across the ring. And so this asymptotic behavior is exactly what we would expect to see, and exactly what we do see when I actually look at this model, which is that the temperature disperses itself. And it's even easy to see that it's an average if you look, that blue ring sort of cuts exactly through where that temperature distribution looks like about half of the area is above and half of the area is below. So how do we use this? Well, let's look at a specific example of a distribution of heat and see if we can use that to figure out what the actual solution to the heat equation is. So here's what we know. We know that if we have ut is equal to 1/2 uxx, then u is equal to the sum from n is equal to minus infinity to infinity of f hat of n e to the minus 2 pi squared n squared t e to the 2 pi I n x. And u of x and 0 is equal to f of x. That's where we get the Fourier coefficients from. Let's look at a temperature distribution that looks like a square wave. Now, it doesn't make any sense to talk about negative temperature. At least for us, what we're thinking about is temperature relative to absolute 0. So I'm only going to specify temperature values that are positive numbers, so relative to some base 0. And so I want my initial temperature distribution, say, to look like 1 if we're between 0 and 1/2. And let's just suppose that it's 0 otherwise. And if I look at what that looks like on a plot, what I'm saying is if you have the ring, the temperature distribution looks like this. So half the bar is heated up to temperature 1, and half the bar has no heat energy in it at all. Find the solution to the heat equation. Well, that corresponds to just finding the Fourier coefficients of f. So really what this question amounts to is find f hat of n for f of x. And that's pretty easy to do. The integral from 0 to 1 of f of x e to the minus 2 pi I n x dx. Well, since f is 0 from 1/2 to 1, I can just reduce this to the integral 0 to 1/2 of e to the minus 2 pi I n x dx. And that looks like 1 over minus 2 pi I n e to the minus 2 pi I n x evaluated from 0 to 1/2, which is 1 over minus 2 pi I n times e to the minus pi I n minus 1. Now, when n is an odd number, this will be -1. When n is an even number, that will be a 1. So this will disappear. This is equal to 0 if n is even. and it's equal to 1 over pi I n for n is odd. It's not so hard to see that that's the case. You should look at it. And I can get the I out of the denominator and write f hat of n is equal to 0 if n is not equal to 0 and n is even. F hat of n is equal to minus I over pi n if n is not equal to 0 and n is odd. And for f hat of 0, I have to evaluate the average value of the function, which is the integral from 0 to 1 of f of x dx, which is the integral from 0 to 1 of 1/2 of dx, 1 dx, which is just 1/2, which is, yeah, 1/2. Not hard to imagine that the average value of a function that's 1 for half the time and 0 for the other half has an average value of 1/2, but there it is. Okay, well, that's enough to write down the solution to the heat equation. So we know then that u is equal to the sum over just the even numbers. In fact, we can be even careful. We can be more careful here and write the following. We could write 1/2 plus the sum over all of the even n's that are not 0 of minus I over pi n e to the minus 2 pi squared n squared t e to the 2 pi I n x. And this is the particular solution to the heat equation with the initial distribution given by this function. And that's it. This sort of combines everything that we've done so far in that we've used the Fourier series to solve the differential equation. We've used the fact that the Fourier series have terms that are orthogonal to isolate the CNs. We've used the fact that we know how to compute Fourier coefficients to write down the specific solution to the heat equation with a specific initial distribution of temperature. And if I want to go further and use a weirder function, I could just use a computer to compute the Fourier coefficients for me. So this is an example of a concrete application of the Fourier series and the one it was invented for. And there's really not an easier way to do this. And so these kind of circular expansions occur in all sorts of situations in nature where we can reduce a problem to thinking about it in these circular pieces where we can parameterize just by angle. The fact that we have the space and time components of the final series separated into these pieces is the core of an idea in the study of partial differential equations called separation of variables. If you can write a series down where the coefficients are determined by time and the spatial components are determined periodically in x, well, one, there's a lot of equations where that assumption holds. And two, that lets us use the sort of full power of Fourier series to do it. So this idea right here, that we can solve a specific, extremely important differential equation, which launches an entire field of the study of partial differential equations, and that we can do it in terms of easy to understand sines and cosines, because remember, these are really just phase-shifted sines and cosines. And these dudes, well, there's no I up in here, so these are just real valued functions. So this is a real valued exponential, and these are just sines and cosines. So everything here is easy to understand. And those are easy to compute for lots of very basic functions that you would use to initially distribute heat over some ring. So there's a lot of different ways that this theory can go from this point. So what we started with here was we had this ring of length 1. And then we thought, we'll take the ring of length 1 and we'll wrap the edges around together and we get this circle. And that's what lets us think about the solutions as being periodic. Well, one idea that we might have is maybe I could use the same ideas to work on partial differential equations or physical scenarios where instead of having the rod being of length 1, maybe I can think of a non-periodic function as corresponding to a rod of infinite length where I take the two ends and I wrap them together. So it's a non-periodic function is really secretly periodic of period infinity. And maybe if we do that, we can take the idea of the Fourier series and turn it into something that will let us deal with non-periodic functions or physical situations where I don't have restrictions on the length of what it is that I'm studying. So that's the core of an idea called the Fourier transform. And that's basically where we're going next with this, is we're going to take the ideas that we've worked out here, where we have everything is restricted to periodic functions, And we're going to try to extend it to functions that are not periodic. All right, so we've sort of reached the end of our first big concrete example of how these Fourier series are used. I want you guys to practice some of these questions, and I'll be posting a video that covers a lot of examples of how Fourier series are used to pull apart and put back together functions of various kinds that go beyond just the heat equation. But this is the core sort of motivating reason why these things turned out to be so powerful. And then over the 300 years after Fourier figured out how to do this, it turned out Fourier series were applied all over the place in all kinds of contexts. And also mathematicians figured out that they actually work. So the mathematical perspective is you can't do it unless we prove it's true. And the applied mathematics and physics and engineering and even mathematicians of Fourier's day approach was, hey, it looks like it works, so we might as well do it. So I want you, for now, to have the same approach. We wouldn't be learning this if it didn't work. So attack it like this is an idea that you can apply in all kinds of contexts, and you won't be wrong. Okay. Read the Osgood chapter that goes along with this, do your homework, and I'll see you for the next video.